Okay, so for part 2 of homework 1-5, we have to pick up here with part B of question 5. We've got to make our position, velocity, and acceleration versus time graphs for this cart as it coasts up the hill and then rolls back down. And again, you could start with any of these. Probably the acceleration or the velocity would be the easiest ones to start with. And in this case, the acceleration actually might be the easiest, because the acceleration versus time, we know while that cart is on the ramp, right, or where that car is going up the ramp, the entire time that it's going up the ramp, the acceleration is working against it, and we found that acceleration from our previous part was negative 1.70 meters per second squared. So in this case, if I actually make my acceleration versus time graph, I'm going to go ahead and move this up here just so I can make my acceleration versus time graph. Maybe this is 1, this is negative 2. I would just be a constant down here at about 1.7 meters per second squared. So my acceleration versus time graph is just a constant. It is a horizontal line at negative 1.70 meters per second squared. So that's not too bad for the acceleration one, and maybe the easiest one to start with. Because the acceleration is a constant and it's negative, that tells me my velocity versus time graph, even if I was just looking at the graph, tells me my velocity versus time graph should be a straight line because it has a constant slope, since the acceleration is constant. Right, we know the slope of a velocity versus time graph is acceleration. And then in general, we know the fact that it started at 30 meters per second, it reaches 0 at the top, and by the time it reaches the bottom, it's to negative 30 meters per second. So it's just the same speed, but in the opposite direction. So then my velocity versus time graph, and I should probably make some tick marks here. So 10, 20, 30, and then negative 10, negative 20, negative 30. And obviously always try to be realistic about this and scale your graph if you can for us, right? And in this case, actually, it would be wise to list the times on here as well, because you could actually figure out how long it takes to go up the hill, so that would be a good idea. I'm not going to take the time to do that here just because I don't want to waste your time on it, but it would be a good idea to do that. But anyway, I know that it's going to travel through, and then at some point, right, so this is maybe what I'll call T1, that would be where it reaches the top of the hill, and then over here at T2, that's where it's back down to the final place at the bottom of the hill again. Okay, so again, I can see that it's just a straight line. It does reach about the same velocity that it began with, but in the opposite direction. So my velocity versus time graph should look something like that. So if my velocity versus time graph is a straight line, what then should my position versus time graph be? Well, you could do this a couple ways. You could kind of find some points and plot it from there. But the easiest thing to remember is just the fact that if my velocity is y equals mx plus b in some form or fashion, then my position graph is going to have to be m divided by 2x squared, right? If I integrated this function, it'd have to look something more or less like that. So the significance here is I'm going to have a parabolic function. I'm going to have a quadratic function. So my position graph should look something more or less like this. Now I know that I'm defining it starting at 0 at the bottom of the ramp at 0 seconds, and then at T1, so I do want to line that up here, so if you want to draw those dotted lines up, so at T1, that's where it's going to reach the highest point, the furthest away from 0, and that's where the slope should be 0 as well, because that's where the velocity is 0. So my curve is going to look something more or less like this, right? I've got a parabola that's reaching up, reaches its highest point at T1, and then it comes back down. And in fact, if I wanted to label T1, I could label this because I know from part A that it reaches 264. So maybe I go up by 50s, something more or less like that, and I would know that this is 264. Okay, so you do want to try to label as much information on these as you can. I know I didn't do that on here, but I trust that you guys can find some values to label these with. But I just want you to be comfortable with the basic shapes as well. So my acceleration would be constant, my velocity would be a straight line with a constant slope, and then my position would be a decreasing slope at first. It would level out at 0 at the peak position up there, and then its slope would actually get steeper in the negative direction as it picks up speed in the negative direction. So a very complex problem, but hopefully one that wasn't too bad. Questions 6 and 7 here are a couple more questions that focus on turning points and just getting comfortable using these functions to help us out. So a particle's position is given by the function that they give us there. Find the turning points for the function, and then the particle's position and acceleration for those turning points. this hopefully is pretty quick and easy. Now, first and foremost, if you had a graphing calculator available, you could actually just graph this function and see when the function turns around. So you could check and see when it does something like that and what is that value for the minimum. But algebraically, if we want to work this, the way that we can find the turning points is we can figure out when does the velocity equal 0 and go from a negative to a positive or a positive to a negative. So in this case, if I want to do that first, I'm just going to find the derivative of that function they gave me. So the derivative would be 2t minus 4, and then the 2 of course would go away since it doesn't have a t with it. So I just need to figure out when does this function equal 0. Well, the only time that's going to happen, right, there's only one t to solve for. So solving this, I would get t equals 2. So that tells me if I'm going to have a turning point, it's going to be at 2 seconds. Now again, this is where I would recommend either graphing this function or graphing this function to confirm that this is in fact a turning point. And it is. This is truly a turning point. And even if you just look at this equation, isn't the velocity function just going to be a straight line here? So it's going to start down here at negative 4 and then go up 2 over 2, or excuse me, up 2 over 1. So it definitely turns around because the velocity versus time graph is going to cross through the x-axis. Not just touch, but cross through the x-axis. So it is in fact a turning point. But I do want you guys to make sure you're stopping and thinking about that for sure. So then part B just asks us what is the position and the acceleration at that turning point. So this is easy enough. Well, the position hopefully is very easy because they gave me the position function, and since I know the turning point was 2 seconds, I'm just going to plug in 2 for t. Okay, so 2 squared minus 4 times 2 plus 2. So I'm just substituting that value in. I get 4 minus 8 plus 2. So I find it to be a position of negative 2 meters from its starting location. Okay, so negative 2 meters is its position. And I shouldn't necessarily say its starting location, but negative 2 meters would be its displacement based on this position function. Anyway, for the acceleration, I still need to find my acceleration function. So to find the acceleration function, I do the derivative of the velocity. Well, if I do the derivative of velocity, I actually just end up with the acceleration function equaling 2. So it really doesn't matter what t value I'm looking for. I could plug in 2 if I want, but that's not actually going to change this value over here. So what that tells me is the acceleration of this particular particle is always 2 meters per second squared, and it is a positive 2 meters per second squared. But this is just a constant acceleration, which, take a second, make sure that makes sense. It's got a constant slope, and its position function was a parabola, so it should have a constant acceleration, right? All of that should be adding up hopefully for us. Question 7 then is very similar to question 6. It does have maybe 1 or 2 little tricks though. Question 7 here, the biggest thing is we want to find the turning point. So again, they actually give me the velocity function this time. So I set 6t squared minus 18t equal to 0. This does in fact have 2 zeros. If I factor 6t out, I get t minus 3. And so then my 2 zeros would be t equals 0 and t equals 3. And again, I want you to stop and make sure you have checked these either graphically or algebraically, but in fact both of those actually would be turning points. Now 0, you could make the argument that that's where the particle started, so is it actually a turning point or not? But if we did project the motion backwards, this would be a turning point for it. So 0, you can kind of tentatively say is a turning point as well. This example is kind of a borderline one, but we're going to go ahead and work with both of these being our turning points. Okay, so anyway, part B then, just like question 6, wants us to find the position and the acceleration at those turning points. So we need to find our position and our acceleration functions. When we start with the easy one, let's actually just find our acceleration function first. The acceleration function, once again, is the derivative of this, so 12t minus 18. So if I want to find my acceleration at 0, well, that's easy enough. It would be 12 times 0 minus 18, so negative 18 meters per second squared. And if I want to find my acceleration at 3 seconds, it would be 12 times 3, so 36 minus 18, which is actually a positive 18 meters per second squared. And do notice that there actually is a little bit of symmetry, right, involved in this. And think about maybe why that would happen. Then we also want to find the position though, right? And that's the part that is a little bit trickier. So to find the position, right, if I have to find the position function, I need to do the integral of my velocity function. Well, to do the integral of my velocity function, I would increase the power and then divide by that new power. So 6 divided by 3, t to the third, minus 18 divided by 2, t to the second. And again, the biggest key here is do not forget the plus c. And I know that's the easy part to forget. But anyway, I get 2t cubed minus 9t squared plus c. Okay, so we do have that c in there, but in this particular example, they gave us a means to find it. They told me that the position, so the position here should be -8 when t is 2. So if the left side of the equation is -8, then I'm going to substitute 2 in for all of those t's, and then I just solve for c. Okay, so in this case, it's just a matter of solving. So 2 times 2 to the third power is 2 to the fourth power, which is 16, minus 9 times 2 squared, which is 4, so 36, plus c equals -8. Okay, so a little bit more algebra here, and you find that c is 12. So what that tells me then is my position function, my actual position function, is 2t to the third minus 9t squared plus 12. So then finding the position, once we have the function, finding the position at 0 seconds is easy enough. The zeros obviously would substitute in and just make this 12. And then finding the position at 3 seconds, a little bit trickier, right? You just have to make sure you're careful on calculating it. But when you plug that in and see what you get, you should get about -15, exactly -15 meters. Okay, so there are my positions for this last question here, or question 7. Okay, so make sure you are very comfortable with finding the turning point both graphically and algebraically, and make sure you are very, very comfortable with how to find C if they give me some information to begin with. Those are some key concepts we want to make sure we have. So this question here is very similar to the one we saw in class. The first thing I'm going to go ahead and do is go ahead and calculate my angle, right? So based on the triangle here, I can find theta as the tangent inverse of 30 over 240, in which case, and that is a 240 by the way, in which case the theta ends up being about 7.13 degrees. And then the directions down here say make an appropriate graph to represent the data, and then what is the experimental value for the acceleration due to gravity. So like we saw in class, the big key here is we don't just want to plot velocity versus distance, because the slope of velocity versus distance doesn't have any meaning. Instead, when I make this graph, I'm going to want to make a graph that is velocity squared versus displacement. Okay, so rather than just velocity versus distance, I'm going to do velocity squared versus displacement. Okay, so all we have to do then is find our velocity squared values because we already have our displacement values. And so obviously you guys can do this pretty quickly here. I'm going to write in the values that I found. So 2.07, 3.10, 4.12, and 4.97. And the reason for that is once we plot all of these points, and again I know you guys can plot points, so I'm going to do this fairly quickly, and I'm going to assume that you can do this probably a little bit better than I can. So I'm going up here, this is 5, and keep in mind the units here would actually be meters squared per second squared for what it's worth. So obviously not perfectly spaced here, but close enough. And then I'm going up by 0.5 meters. Oops, so that would be 1.5, 2.0, and 2.5. So this is a 1 here. And again, those are meters. So if I plot my points, right, ultimately I should get something that's fairly straight line, right? I get something that's just more or less like this, which tends to be a relatively straight line, right? Obviously you could use an actual ruler, but that would be a straight line going through it. So the significance here though is if I'm thinking in terms of this equation, the slope of that straight line is going to represent my 2 times a in this equation. Since this is my y value, and this is my x value, and this would be my v, my b, which is my starting point, then the 2a would equal my slope. So then I just need to choose any 2 points along that line. I ended up choosing, I think, the first point of 1 and, or the 0.5 and 1, and then I chose the final point over here of 2.5 comma 4.97. I found my slope to be 1.985, which means my acceleration then was that divided by 2, so it was 0.9925. And then if I plug that in to find my actual g, I find g to be about 8.0.